So hi, my name is Sam Rubenstein. I'm a security analyst and hacker at the Cisco Security Threat Analysis and Reverse Engineering Center in Israel. Our center performs security evaluations of Cisco and third-party products, including work for external customers. We mostly evaluate the security of black box devices, embedded black box devices using a black box model. So we don't have access to source code or architecture documentation or anything like that. We basically just get boxes and are told to hack them. Let's start off today with a quick demo. What we're going to do is I have here on my desktop the Twitter application running, okay? And I'm going to run Frida trace on the Twitter application. I'm going to tell it that I'm interested in all functions which begin with open. It's going to tell me that it auto-generated handlers for a bunch of different functions, okay? And then that it started tracing 27 functions. If I now go to Twitter and pull down to refresh the list, I see a whole bunch of opens. There are different colors because each thread has a different color coding, so that you can easily pick out which function call happened on which thread. But we can see there's a whole bunch of different open function calls here. What actually happened is that Frida generated a __ handlers directory, okay, within which there are the subdirectories for each of the modules which we hooked. And if we look at, for example, the libsystem bdylib, we'll see that there are JavaScript files for each of the functions that were hooked by Frida. So if we go and edit the OpenJS handler, what we see is that there's a JavaScript object here defined, okay? And there's a whole bunch of comments so that you can easily get started with this stuff, but that's not really important at the moment. What's important to note is there's an onEnter function defined, which receives log, args, and state. And that onEnter function just logs open with empty braces. And there's also an onLeave function, which gets log, retval, and states. Okay? If we come here and say, we know that the open POSIX call has a first argument, which is the file name of the file being opened. So let's try and print that information. We can just go args 0, okay, to print the first argument. We'll save that. And one thing that's pretty cool about Frida is that it automatically watches the files that it's generated. So you don't have to worry about restarting the trace. You can just pull down on Twitter again to get it to refresh, and we get new information. We now get the pointer printed for each of the open calls. Pointers are great, but they're not really that easy to understand. So let's see if we can get the actual data for that pointer. What we can do is that we need to read the memory at that pointer. We know that the pointer is a pointer to a UTF-8 string, so we can use the memory.read UTF-8 string function to read the memory at arg0. If we save this again and then pull down once more, we now get the full path name of the files being opened. We can already see that Twitter is using Crashlytics for crash analysis. And if we wait a bit, we'll see, caching of various images and stuff like that. So we can immediately tell a whole bunch of stuff about our application just from hooking one open call and making a simple JavaScript change to the open handler. What's even cooler is that I have here an iPhone attached. Okay, and if I stop the tracing and instead of saying Frida trace Twitter -I open star, which traces the Twitter application running on my desktop, on my laptop. If I add the -u arguments, okay, for USB, it now traces the Twitter application running on my iPhone. If I pull down here, we'll see the same scripts being used on a completely different platform, completely different application, completely different platform. So, what just happened? What did we just see? We saw that using Frida, we can trace and instrument arbitrary functions in processes. We can attach onEnter and onLeave handlers to functions. OnEnter will occur before the function runs, and onLeave will occur after the function's finished. We can even completely replace a function with a function of our own, a JavaScript function of our own. Frida actually lets us also instrument any function in the target process. Using Frida trace, we can trace objective-C method functions, methods, functions, class methods, instance methods. We can trace functions by pattern. Like you saw, we said open star, and it globbed it so that you could trace by a pattern or name. You can even specify a module and an offset. If you know the address of a function within module, you can use a module and offset to trace a function. And in fact, you can even get Frida to instrument arbitrary function addresses, arbitrary instruction addresses, not just function boundaries. Our instrumentation code is in JavaScript. This JavaScript actually runs within the context of the target process. So it has full access to all the process resources like memory, file descriptors, sockets, loaded modules, etc. Having the instrumentation code in JavaScript lets us eliminate the compile, load, retry cycle that you need with most other tools. For example, techniques like LD preload, you'd have to compile your C code, load the code in the target executable, retry, and every time you want to make a tiny change, you have to go through that whole process again. You saw how quickly and easy it is to make changes to the trace handler, and we don't even have to restart the trace. It will automatically be applied with Frida. Also, with the in-process code written in JavaScript, we can conceivably use the same in-process script for different architectures and platforms, like we saw with the iPhone and Mac OS. We saw that we can live edit the handler scripts generated by Frida trace, with changes to those scripts being immediately and automatically applied, without needing to start and restart the trace. This further reduces the implementation or instrumentation cycle, exploration cycle. So what is Frida exactly? Okay. Frida is like greasemonkey for native applications. It's an in-process binary instrumentation framework. It's in process because the instrumentation code runs within the process, unlike with GDB where you attach from outside and you're working from outside the process on the process. With Frida, your instrumentation and exploration scripts run within the process, within the context of the process, so you have access to all the process resources as a first-class citizen. You don't have to worry about permissions or anything like that. It's binary because Frida works on compiled binaries without any need for source code or compile time instrumentation. It uses techniques like inline function hooking in order to implement its functionality. Frida provides tools and functionality for instrumentation and exploration of target processes, allowing for advanced dynamic analysis and debugging with easy-to-use scripting. Lastly, Frida is a framework. It's intended to supply the necessary base functionality and tooling to allow you to build your own tools on top of Frida. In fact, Frida's license expressly permits the development and distribution of tools, be they open source or proprietary. So even if you want to take Frida and build your own proprietary applications on top of it, that's great. Frida is happy to have that happen. Frida is multi-platform, multi-arc. It lets you instrument processes on all the major platforms and architectures. Because the in-process code, which actually runs within the process, is in JavaScript, it's very portable as well. And you can use the same instrumentation scripts across multiple target architectures and target platforms. Like you can see, we have Linux, OS X, Windows, iOS, and Android, as well as QNX. We have good support on all the platforms where there is support for the platform itself. There's just some Windows, I don't know if there's actually support for Windows on ARM, but just Windows and ARM that isn't supported, and Linux ARC64 because we haven't encountered that kind of target yet. Frida is self-contained and does not require any modifications to the system it's running on. In fact, you can even use Frida on non-jailbroken iOS devices and unrooted Android devices. Frida is fully open source with a very active community led by the creator of the project, Andrei Vadlaravnas. It is under constant development to provide both better platform-specific support and new and improved functionality and APIs. The framework provides language bindings for Python, C, Swift, and Node.js. So you can build your applications, your debugging tools, you can build them on top of Frida in the language of your choice, more or less. And you can use the language which is best suited for the particular task at hand. Frida is built from modular components, which can be used independently of one another. This further enhances the functionality and the way that you can use Frida to build your own tools. So we've said that Frida is a framework or toolkit on which you can build your own tools, but Frida also comes out of the box with a bunch of utilities and tools to get you started instrumenting and exploring processes right from the first day. Most of those tools are written in Python. We've already seen one of those tools, Frida Trace. Let's take a look at some of the other tools that are available. Okay, so the first tool that we're going to look at is Frida LS Devices. Okay, Frida LS Devices is a tool that lets you list the devices that Frida knows about on which you will be able to attach to processes. So what we have here is we have the local system, which means that we can attach to processes running on this Mac. We have a local TCP, which is actually used to connect to remote hosts over a TCP connection. And we have an iPhone attached with the specific device ID. You can use the -D flag and the device ID if you have multiple iPhones or Android devices attached. You can use the -D flag on the other Frida tools in order to specify which device you want to connect to and to attach to. The next tool is Frida PS. Frida PS lets you list the running processes on a target device. If we run it without any arguments, it will list the processes running on the local system, in this case my Mac. You can see the processor's name and the PID for each process. If we add the -U flag, we're asking Frida to use the USB, and now when we list processes, we're listing the processes running on my iPhone. If we add the -A for applications and -I flag for installed, we'll list the applications which are installed on the iOS device with the PID for running already, the name of the process, and the application identifier so that you can identify which applications are running on your devices. Excuse me. The last tool that we'll look at is a REPL. Okay, we just have the Frida application itself, which is a REPL, a read, evaluate, print loop utility, which basically gives you a shell. If we run Frida with Twitter, we'll see that we attach to the local machine to the process named Twitter, and we have here a shell. Okay, if we hit tab, we'll see all the APIs and objects that we can use to access Frida's API. This is just a JavaScript REPL with added APIs from Frida. Now, every expression that you run on this REPL in this command line is actually executed within the process of the target process that you're instrumenting. If we, for example, want to look at the process and enumerate the modules that are loaded into this process, we can use the process enumerate module sync function. And here we get a listing of all the modules that are loaded into this app process, including the base address, name, full path to the file, and the size of the image. We can also do things like module.findExportByName, which will find a exported function in a given module by the name that you provide. So if we know that we want the libsystem b dilib module, and we're interested in the open function, if we do find export by name, we get the address of the open function as it's exported from the libsystem b dilib. Now, if we don't know which module exports a given function, or we just are lazy, we can just drop null in here as the first argument, and then Frida will go ahead and look at all the modules and will find your export in the module that it is. There's also very powerful objectivec support. You can, for example, go objectivec.classes, and here we have a drop-down of all the objective-C classes that are known to the process, i.e. all objective-C classes that are loaded in this process. If we start with Twitter, for example, we'll see that there's a bunch of Twitter objective-C classes available here for us to explore and instrument. We can also perform interceptor attaches, okay? Interceptor attach will actually intercept a given function and attach on enter on leave listeners to that function. So we can say interceptor.attach module.findExports by name, null, we're interested in open, okay? And then we'll say we want an onEnter handler, which is a function which receives arguments. And here we can print with console.log open calls. Okay, we've now implemented our interception. If we go to Twitter and pull down, we'll see a whole bunch of open calls. Okay. Now, that's really awesome, and it's very useful for exploration and quick discovery of what's going on within an application. But it's a little bit more painful to write longer expressions like the one that we just wrote on the REPL itself. Thankfully, Frida's REPL allows you to load from a script file. So that's what we're going to do now. We will write a file called explore.js, and we'll drop the same interceptor attach module.findExportByName null, because we're lazy, and open. And then it's a lot easier to read it when it's like this. We have an onEnter function, which has the arguments of the function call. Okay, and here we can log open calls. Okay, and now if we quit the REPL, and this time load it with -L, load the explore.js script, it attaches and runs our script, and we can now see open called when the open is called. Now, one thing that's important to note is that Frida does not know anything about the function that's being intercepted. You don't have to specify the calling convention, you don't have to specify the number of arguments, you don't have to specify the type of arguments. Frida is completely agnostic to these things. It doesn't care about them at all. It performs inline function hooking and gives you access to the arguments via the args variable, args parameter, using the given platform and architecture's standard calling convention. So on ARM, you have your first 4 arguments in registers, and the rest are on the stack. And x86, your arguments are on the stack. All that information is abstracted by Frida, and you can just access the arguments via args. Okay? If, however, you have a function which you know is doing something strange, is using a non-standard calling convention, or you just want to be able to access the processor registers at the time that the function is called, you can access those things via the this.context object. We can, for example, look at RDI, which is the first argument on x86-64. If we console.log that, we get the, oh, wait. Okay, we get the pointer in RDI. Okay, the pointer is not really that useful for us, so let's once again print the contents of the pointer instead of the pointer itself by performing memory.read UTF-8 string on the pointer. And here we'll reload and pull down. And now we get the full path again. Now, that's cool. We can see what files the process is opening. But we'd like a little bit more context than that. We can use a cool feature of Frida that's called thread.backtrace. What that will do is it will take this context and it will generate a backtrace like you'd see in GDB for the point at which it was called, which you call thread.backtrace. Okay? So let's try that. We'll pull down. And now we get a list of pointers for each call. That's the backtrace, the pointers. But pointers are difficult to understand. Let's see if we can make it a little bit more simple. The thread.backtrace function returns an array of pointers. Okay? So what we can do is we can use a standard JavaScript map function to map the debug symbol .fromAddress function onto each element in that array. Then we can just join that resulting array with new line and tab just to make it a little pretty. We can reload again and pull down. Takes a little bit more time this time just because it has to calculate the debug symbols. And now you can see backtraces that really give you a very good picture of where in an application your opens are occurring. So all of these little tricks, you saw how in a couple of minutes we've managed to get a lot of context about a given call, which can be very useful for us understanding the process that we are targeting. While demoing the REPL, we actually started looking at the very rich JavaScript API that Frida makes available to your JavaScript instrumentation scripts that are running inside the target process. This API lets you interact with and explore the application as it runs. Frida's API is also memory safe, So if you, for example, try to do memory.read UTF-8 string on a garbage pointer, or 0, or whatever it happens to be, your process won't crash. Frida will catch that and handle it gracefully. So you're safe and you don't have to worry about your target process caching. So now we've got a fairly good idea of what we can do with Frida. It's pretty cool, but let's try and do something real. Well, let's try and make our understanding of Frida concrete by performing a real task. What we're going to do is we're going to intercept the network traffic of Twitter, and we're going to simply uppercase every tweet as it comes in. So we're basically going to shoutify Twitter, okay, or yellowify, you might say here. And what we're doing is we're just modifying the network traffic as it comes in, and because we're modifying that network traffic, the Twitter application will see our tweets as shoutified. So first we have to work out how tweets are actually delivered to the Twitter application. So let's start with Frida trace on the Twitter app. Now we have to think a second, how is Twitter likely to be connecting to the network, connecting to the Twitter API to download tweets? Now, because it's a native OS X application, it's almost certain that it's using the NSURL request, NSURL connection classes to access HTTP or HTTPS resources. Okay? So what we're going to do is we're going to say -m. We're interested in objective-C methods. Okay? We're interested in both class methods and instance methods. So we'll put a star where the minus or plus would be. Okay? And then we can say we're interested in NSURL connection, okay, as the class. And we're interested in every function. We don't going to be very selective at this point. We just want to see everything that's going on. Okay? You can see again, it's easy to glob, easy to guess what the application is doing. We'll attach. Again, we see a whole bunch of handlers are generated, 46 functions. And now when we go here and pull down, we'll see that we have the NSURL connection in it with requests and delegates. Okay? And that NSURL connection in it with request calls an internal in it with request. Sorry. In it with request function with a delegate and some other arguments. And that is basically the mechanism that they're using in order to download the tweet data. So what we're going to do is we're going to go and look at this init with request. We'll look at the internal one so that we don't miss anything. But we can't really understand what's going on here because we don't know what URLs they're requesting. So let's go ahead and try to work out what URL each of these NSURL requests, NSURL connections is actually trying to connect to. So what we'll do is we'll go here and we'll edit the handlers. Here we have NSURL connection underscore init with request. Once again, we have the onEnter and onLeave functions. Note that Frida has made a guess for the names of the arguments in this function, in the log, because in Objective-C, the function argument names are part of the function prototype, part of the function name. So we know what they are, so we can guess them, and Frida can output, like it did here, can output the arguments one after each other at the right place in the print. So notice that our arguments start here at args2. That's because Objective-C functions have the first argument is the self, or this pointer, and the second argument is the method selector, which selects which method is actually being executed. So we have to skip 2 in order to get to the actual arguments to the Objective-C function method. So if we go and look at the NSURL connection in it with request documentation, init with request documentation. Okay, we can see that the request parameter is an NSURL request object. Okay, what we needed to do is we need to tell Frida that this first argument is an objectivec class instance. So what we do is we say objectivec.object on args2. And what this does is it tells Frida that we want to treat this pointer as an objectivec instance. Then we can access the properties and methods of that instance by simply calling properties and methods on the JavaScript instance. Okay? Now, init with request receives an NSURL request. So let's click on NSURL request to get its documentation. We're interested in the request properties. So we're going to click on getting request properties. We'll scroll down a bit, and we'll see that there is a property called URL, which gives us the request's URL, which is exactly what we're interested in. Okay? So we'll go here and we'll say dot URL, because we want the URL property. Okay? The URL is an NSURL object instance. Okay? So let's click on NSURL to go to its documentation. Okay? We're interested in the URL itself, okay, that's being used. So we can click on accessing the parts of the URL. Okay? And the first property here is something called absolute string, which gives us the URL string for the receiver as an absolute URL, okay? Which seems to be exactly what we want. So we'll add .absolute string. Okay? Now, the absolute string is already an NSString object. Frida knows to automatically convert between NS strings and JavaScript strings. So we're done. We don't have to worry about retrieving the bytes from the NS string. So if we go here and save our file, and we go and we pull down on Twitter again. No, it didn't pull down. Okay, pull down. We now see that with init with request prints the full URL that we're trying to access. So that's cool, but we're actually interested in the payloads of these requests, the data that's coming down from the server. So we're going to move to Frida with a script now, because it's easier for us to write more complex code, more complex instrumentation code in a script file. Not within the Frida trace context, because we're no longer going to be just tracing. We want to actually perform some analysis of the classes and instances to get the data that's coming out of the system. So we'll just start a new file called shoutify.c.javascript. Okay? And the first thing that we want to do is we want to get the handle to the objectivec method that we're interested in. Okay? Before we saw find export by name, JavaScript methods are not necessarily exported by the application, so you can't just use find or export by name. Okay? But the objectivec API in Frida lets you easily access those classes and methods. So what we do is we say objectivec dot classes dot NSURL connection. Connection. Okay, and we're interested in the internal init with requests function prototype. I'm just copying it from here. Okay, and now we'll delete the argument values to get the method signature. The reason I have to do this is because this is an undocumented internal function, internal method. So Frida has no problem enumerating and accessing internal undocumented methods, but we have to, copy the data like this, the name like this, because we can't just copy it from the Apple documentation. Okay. And we need to have here a minus because it's a class method. Okay? We now have a method variable which is pointed to the instance variable, to the class method init with request, delegate, etc., etc., etc. Okay? So now we want to intercept that method. So we go interceptor dot attach, and we'll go to the method's implementation. Okay? And we want to hook the onEnter function. Okay, and what we're going to do is we're just going to say console.log NSURL connection, and we're going to once more have our objectec.args .objects args2 .url .absolute string Okay, we'll save that, and now we'll rerun Frida on Twitter with the Shoutify scripts. We're attached, let's pull down, we pull down, and we see our NSURL connection being hooked. Now, the way that NSURL connection works is that it implements access to network resources asynchronously. What happens is you pass to the function NSURL connection init with request, you pass a delegate object, a delegate instance, to that object, and the objectec function class NSURL connection will call methods on that delegate object when data is received from the server, for example. Okay? The delegate needs to implement the NSURL connection data delegate protocol, and what we're going to do is, what we want to do is we're going to implement a proxy object, okay, which will insert at NSURL connection creation time, i.e. at the init with request delegate creation time, call time. We'll insert a proxy object which will sit between the original delegate and the NSURL connection implementation, okay? And that NSURL connection that proxy will implement the NSURL connection data delegates protocol. Okay? It seems complicated, but it's actually really simple. And it's relatively easy to do in Frida as well, because all we have to do is go var myDelegates is equal to objectec.proxy.registerProxy. Okay, and we want to tell it that we're interested in implementing these protocols, the objectec.protocols, which gives us a list of all the protocols that are available in this application, .NSURL connection data delegates. Okay? We can obviously implement more than one protocol, that's why we have a list there. Okay. If we save that, okay, and then come over here into our onEnter of the method implementation, and what we want to do is we want to switch the arguments for the delegates with an instance of our new delegate proxy, okay? And so what we do is we say args3, which is the delegate, is equal to new myDelegate, and we'll wrap the original args3. We'll pass empty context. Okay? Now our instance will be sitting in between the NSURL connection class and the actual delegate, the original application's delegate. Okay? Notice how we just use JavaScript's new instance call, and behind the scenes it will automatically be transformed into the correct Objective-C magic that needs to happen in order to create an instance of our object, our Objective-C object. It's all transparent from our perspective. Okay? Let's reload and test it again. Okay? We see that nothing additional actually happens. Why? Because although we've implemented a proxy object and we've inserted it between the NSURL connection class and the original application delegate, we haven't actually done anything with any of the methods. Okay? We're interested in a method called connection did receive data. Okay? That's a callback that is called on the delegate when the Nsurl connection class receives data from the upstream URL resource. Okay? Now what we do here is we say, okay, we want to handle the connection did receive data function. We have two arguments, the connection and the data. Okay? So we'll say that this is a JavaScript function which receives a connection and data. Okay? And the first thing that we're going to do is we're going to log console.log in connection did receive data. Okay? And then what we're going to do is we want to now, we've hooked the method, but we want to pass on the connection and the data to the original delegate object as well. Okay? So that the application will receive the data. Okay? So what we do is we say this.data.target.connection did receive data, and we pass on the connection and data to the original delegate instance. Okay? If we reload and pull down, oh, I've made a mistake. Yeah, this is missing an S, methods. Why didn't anybody notice? I'm disappointed. Let's rerun Twitter. Okay, and we'll restart Frida, and we'll pull down. Okay, and now we're receiving our in connection did receive data. So now our mechanism is working. We're able to hook the asynchronous callbacks that are sent by an NSURL connection. Okay. Because it's asynchronous, we might get these in connection did receive data prints at any time, and we don't know necessarily which NSURL connection, which URL resource they're related to. So let's print the URL that is related to the specific in connection did receive data callback. Okay. Again, this is relatively simple. We'll just go console.log. Oh, we'll save it in a variable because we'll need it later. var URL is equal to the connections current request which is a NSURL request. So we know we can go URL, and we can go absolute string. And now we want to actually force it to cast to a JavaScript string. OK? Let's log that. And we'll save, and we'll reload, and we'll pull down. Okay, and now we get the URL of the particular in connection did receive data. Let's look at the data itself. That's what we're interested in, right? But we don't know what format the data takes. So what we'll do is we'll hexdump it so that we can see what it looks like. So we'll just go hexdump of the data's bytes, which gives you, from the NSData object instance that we have there, it gives you the actual byte array in memory. And we'll say that we're interested in the length being data.length. Reload, pull down, and now we get a hexdump of the actual data being received. Now, there's just 2 bytes here, and it looks like an empty array. Okay? Now, this makes sense, because if we look here at the URL that's being requested, it says hometimeline.json. Okay? So it makes sense that we have here a JSON RPC API. Okay? Or REST API, I don't know if it's REST exactly, but it's a JSON-based remote procedure call mechanism. Okay? So we actually know that this data is going to be a string, so we don't have to bother with the hexdump. We can go right ahead and read it as a string. So let's do that instead of the hexdump. We'll go var data in is equal to memory.read UTF-8 string on the data's bytes. Now, because this is being delivered over the network and has explicit length in the content length header of the HTTP request, or response rather, it's not necessarily a null terminated string. So we have to tell the memory.read UTF-8 string function how long the string is, otherwise it will append garbage, or we'll try to decode the garbage. So we'll just go data.length here. And let's print it. So we'll go console.log, data in, and data in. Save, reload, pull down, and now we see the data in. Okay? But at the moment, we're only getting blank data in because there's no tweets coming to this account. So let's send a tweet from an account which is followed by the account that we used to log into the application and see what an actual tweet looks like. So I have a Twitter account here, which is used for testing. And we can say, OK, hi there, besides, right? And I'll just show you that when I tweet that, it's immediately received by the Twitter application, but there's no activity. It's kind of strange. What's going on over here? Let's try a mention. Maybe mentions are treated differently. So we'll go, yo, dummy test 4004. What's up? Right? And we'll send it, immediately received by the application. Once more, no data. What's going on? So if we think about it, and if we were Twitter, we wouldn't actually want to implement an API which would have to do polling of a server in order to retrieve tweets. Okay? for two reasons. First, it means that there's a delay between the tweets being published and then being received by the client application. And also, if you have a polling mechanism, that means that there are millions of users out there who are hammering your HTTP server all the time in order to get new tweets. So instead of doing that, what they do is they have a long-lived connection. They connect at the beginning of the application's lifetime to a given HTTP API endpoint. And then what happens is they wait for new bytes to come down that pipe. And that way, the Twitter backends can actually push data down the HTTP connection to the Twitter application. Okay? Even though there's no push channel in HTTP 1.1, they can use this long-lived connection mechanism in order to do this kind of behavior. So what we need to do is we need to hook the function NSURL connection in it with request at the very beginning of the Twitter application's lifetime, okay? In order to be able to hook that instrument that long-lived connection. So what we want to do actually is instead of attaching to a running instance of Twitter, we want to spawn Twitter on our own. That's okay. Frida knows how to do that. We'll stop the Frida RePL, and I'll just quit Twitter here. And now we'll go Frida, and we're interested in running the Twitter application, but we have to specify that full path to the executable now. Okay? And we're interested in loading a script called Shoutify. Okay? And we'll run that. What just happened? We executed the Twitter app, but we executed it in suspend mode. So the first instruction of the Twitter application has not yet been run. Okay? What Frida has done is it's run it in suspended mode and then given us control, run our little scriptlet Shoutify in the background and dropped us on the REPL so that we can make additional changes if we want to the environment before Twitter has actually started running. What we have to do to get it to run is we have to use the resume command, magic command, and once we hit resume, the Twitter application will actually load. We'll hit resume, and we see the Twitter application loaded. If we look in our output, we see a whole bunch of activity now, okay? But let's now send our tweets. Hopefully we should see this. Okay, received them immediately, and this time I have to decrease the font a little bit, sorry. Let's try that again. Just clipping off the side there. Okay, here we can see the text with the tweet text there. So now we're seeing tweets. Awesome. What are we trying to do again? We're trying to Shoutify? Ooh, okay. What we're trying to do is we're trying to Shoutify the application. So what we're going to do is very, very quickly, because I'm running out of time, we're just going to use a, we're going to say if the URL dot, if the URL dot index of user.json, i.e. if we have the user JSON in our URL string, we'll do var data out is equal to data in dot replace, and we'll use a regular expression just to modify the text. We're looking for text colon not the star And we want to find all of those, so we'll drop a -g. And what we'll do is we want to call a function which receives all A, B, and C. Sorry that I'm rushing this, I'm just running out of time. And what we'll do is we'll return A plus B dot to uppercase plus C. Okay. We'll print our data out. Okay. If we have to restart Frida and the Twitter application again because we've made modifications to that. We'll run that. We'll resume. Wait for it to finish loading. Initial loading. Okay. Tweet some garbage. Okay, and now we see that the text is shadified. But it's still not shadified in the application. Why? Because we haven't passed that information on to the original delegates. Okay, so what we need to do is we need to create an NSData object instance with that new data in order to pass it on to the override the original data. So we'll say data is equal to objectevc.classes.nsData. And we're going to use the data with bytes length function to take the data out and the data out's length. Okay? Now the thing is we can't actually just pass data out because data out is this JavaScript string. We need to give this function a pointer to a C string or UTF-8 string. So what we have to do is we have to actually allocate memory within the target process in order to pass this string on to the NSData constructor. That's not a problem. All we need to do is go var a is equal to memory.alloc UTF-8 string, and we'll pass it our data out string, and it will generate the UTF-8 string at a new location in memory. And now we can pass that on to the data with bytes. We'll stop the Frida and Twitter, rerun it, resume, and just over here we'll wait for it to calm down a bit, and we'll type this should be shadified. And boom. Awesome, right? Our entire script is, what? 20-something lines of JavaScript with all the debug output. Okay? So that was pretty cool. So just to summarize, I hope that this short presentation, which is really short, just an hour, has demonstrated the power of Frida and the utility that it provides and the functionality that it provides in order to be able to instrument target processes using relatively easy to write JavaScript functions. Okay? It really does provide the capabilities to explore, attack, and build useful tools around processes. Obviously, there's a lot more to Frida than what we've shown just now. There's a lot more functionality. We haven't shown the app running. We could have used the same hooking mechanism on the iPhone app as well. But there's plenty more to learn in Frida. I recommend that if you want to find more documentation or tutorials, you can hit up Frida's site, frida.re, or you can find us on GitHub at github.com/Frida. If you want help getting started, or you've encountered some difficulty, or you think you found a bug, because there are bugs. If you think you found a bug or whatever it is, you can either contact us via issues on GitHub, or we're very active in the Frida channel on Freenode, IRC channel on Freenode, and we're happy to help anybody who needs help there. That's all I've got. Questions, anyone? Excellent. So thank you.